And now to today's presentation. Today we're pleased to have Jennifer Hay joining us as our presenter. Jennifer is a factory applications engineer with Agilent, located in Oak Ridge, Tennessee. Jenny's current responsibilities include training field application engineers and developing new applications. All right, I believe we are ready to begin, and it gives me great pleasure to welcome Jennifer Hay.
Well, thank you, Rita, and good morning. And I extend my warmest welcome to everyone who's attending online. My name is Jennifer Hay, and I am the instructor for what I hope will be a comprehensive class on the topic of instrumented indentation. So I often have the opportunity to teach classes on instrumented indentation, and as much as I enjoy doing this, I'm always constrained by time. Sometimes I have as long as 2 days, and sometimes I have just a few hours. So I always have to decide what to cut out, what to gloss over, and what to address in depth. So Agilent has been gracious enough to give me this venue to really hash it all out, starting from the very beginning. So in this class, which will be held on the first Wednesday of each month, I plan to take my time and cover everything that I want to cover. We'll take a lot of side roads, but in the end, what I hope to achieve with this video series is a comprehensive presentation on the topic of instrumented indentation. We're going to at least look at all of the topics that I have listed here, including test and measurement philosophy, definition of instrumented indentation and its relevance, material properties and engineering, basic contact models, both elastic and plastic, measurements, semi-static and dynamic, advanced models, including both computational and theoretical models, and applications and user-suggested topics. I strongly encourage everyone, even if you're listening to a recording after the fact, I strongly encourage everyone to suggest topics for this series. And if it's a good topic and it fits, but I don't feel like I have the expertise to address it, then I'll just do my best to get a guest speaker to cover it. So we welcome your ideas for topics in this series. All right, before we get into the class, I thought I'd take some time to introduce myself. I have bachelor's and master's degrees from the University of Houston. While I was a teaching assistant there at the University of Houston, I won a university-wide award for teaching excellence. I have worked in the field of instrumented indentation since 1996. I began working for a company called Nano Instruments, which was the original company founded by Dr. Warren Oliver and Dr. John Pethica. I was actually only the 13th person to be hired, and my first responsibility was to work in the contract testing lab we had at the time. I remained with the company through the acquisitions by MTS in 1998 and Agilent in 2008. And I currently hold the title of Expert Scientist for Agilent Technologies. My office and my lab are in Oak Ridge, Tennessee, and I actually continue to work closely with Dr. Warren Oliver and other founding members of Nano Instruments. Within Agilent, my major responsibilities include developing and publicizing new applications for instrumented indentation, usually in collaboration with university researchers. I am also responsible for training our applications engineers in the field. So I've been doing this for a while, closing in on 20 years now, and I still love it. I think this is still a dynamic area of research, both with respect to the development of the test and measurement technology itself, and with respect to its application for new materials. On this slide, I have listed some of my most recent projects just to give you the flavor of my interest. I developed a test method for measuring the complex shear modules of gelatinous materials, and if you're interested in that sort of thing, you can follow the link I have there to read more about it. I work together with the researchers at Erlangen University, specifically Ms. Karina Meyer, and that's in Germany, to implement a new test method for measuring the strain rate sensitivity of metal by instrumented indentation. We have a new product option called Express Test, which I think is going to revolutionize the field. What this product option does is allow you to do indentation testing at a rate of 1 indent per second, and that includes the approach, the actual indenting, and moving to the next test site. So if you can imagine, you know, indent, 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 like that. Express Test just opens up a world of testing possibilities, so I've had a lot of fun doing the verification and application development for that product. A couple of years ago, I was invited to write a feature series on instrumented indentation for the journal Experimental Mechanics, and so far I've written 3 articles for that series, and I'll probably make good use of those articles in this class. And finally, I developed an analytic model for measuring the substrate-independent modulus, Young's modulus of thin films. That work was published in the Journal of Materials Research, and it received a Best Paper Award from the Society of Experimental Mechanics. So those are some of my more recent projects. In the next year, I really hope to get back to focusing on ultra-compliant materials, gels, and especially biological materials. So if there's someone in our listening audience today who has complementary interests, I'd definitely like to hear from you and begin a conversation about possible collaboration. All right, so aside from small-scale mechanical testing, my other major academic interest is in philosophy and history of science. So these kind of questions really interest me. I like to think about what science is, how real scientists do science, how does test and measurement contribute to and benefit from science, what can we learn from past scientific debates, how does science relate to other cultural activities, and how do we know what we know, which is a field called epistemology. So just last week, I finished reading Michael Polanyi's flagship book, Personal Knowledge, which has me absolutely memorized. So I have to confess all that up front because it's gonna that interest is going to make its way in and out of this class, I think. And finally, this is a picture of me with my most of my immediate family from our Florida vacation last August. This is me on the left. This is my 3-year-old son and my 12-year-old daughter and our dog, our family dog, and my 4-year-old daughter. I also have a 20-year-old daughter who wasn't with us on this vacation, and my husband, as always, is behind the camera. All right, so that's definitely enough about me, but I'm not quite ready to get into instrumented indentation just yet. I want to begin with some philosophy, especially as it relates to the discipline of test and measurement. And I can do this because, for once, I'm not pressed for time. So, although René Descartes would dissent from this statement, I'm prepared to follow Aristotle and Aquinas and Polanyi in affirming that sensory perception is the foundation of all scientific knowledge. Now, what do I mean by science? At its most basic level, science seeks to explain reality. In other words, given any real being, whether it be animal, vegetable, or mineral, what we want to know is what it is, how it interacts with its environment, and finally, what phenomena caused it to come to be as it is. So around 400 BC, Aristotle established for us the epistemological progression of science. In other words, he established how we come to know what we know in science. And in the flow chart on the right here, I've tried to illustrate Aristotle's hierarchy of knowledge. First, we have reality up here, real beings that we want to understand and explain. And we perceive reality with our senses. And then by means of memory, we integrate perception to form experience. And then we make sense of this experience by means of theory in order to achieve knowledge. And we call science that accumulated knowledge which apprehends reality. Now, I would like to point out that this progression isn't just chronological. Each step in this process is progressively more and more communal. In other words, my knowledge about, say, diamond does not have to come from my own immediate sensory perception. It may come by participating in a community in which I trust that others have adequately sensed and integrated that sensation to form reliable knowledge. Nevertheless, that knowledge had to begin with sensory perception at some point, even if I'm not the one actually doing the sensing. So in summary, if we want to do science, if we want to explain a thing, we really do have to first see it, touch it, hear it, taste it, etc. So what exactly is it that we perceive with our senses? And here I agree with philosopher Norris Clark. What we sense is always some kind of action. He says it is through action and only through action that real beings manifest or unveil their being. Action is precisely the self-revelation of being. And not only are we receiving action, but in the process of sensing, we ourselves are also acting. So, in general, sensory perception involves interacting with reality. In other words, it involves both acting and being acted upon. Okay, so sensory perception really is the foundation of science, but there are some definite limits to sensory perception. The first limit is that the action or phenomenon may not be immediately available to the human senses because it is too small, remote, or sparse, or outside the operating domain of our senses. The fact is our eyes are not sensitive to X-rays and infrared radiation and all that. There are some phenomena that are simply outside the operating domain of our senses. And then the second objection that we have from Descartes is, I have noticed that the senses are sometimes deceptive, and that's true. And finally, our memory is limited. And this is where I think that test and measurement comes in. Test and measurement enhances sensory perception. A test involves acting on a real being in a quantified way. Measurement involves quantifying the resulting interaction. Test measurement enhances and quantifies sensory perception. It makes phenomena or action available to our senses which otherwise would not be. And finally, data acquisition and recording mechanisms enhance our memory, leading to a more broad-based experience. And so on this side, I have some examples of how test and measurement enhance and quantify sensory perception. For example, microscopes and telescopes enhance our sense of sight. Oscilloscopes enhance our sense of sight and hearing. Analytical chromatography enhances, I think, our sense of smell and taste. And it is my contention that mechanical tests, including instrumented indentation, enhance our sense of touch. So to summarize, my view is that the discipline of test and measurement complements sensory perception. Now, note I said complements, not replaces. It complements sensory perception by extending and quantifying it. Because the discipline of test and measurement extends sensory perception, it enhances the very foundation of science. And of course, the relationship is reciprocal. Test and measurement itself benefits from scientific advancement. So why begin with philosophy? Well, the first thing that I hope to communicate here is my passion for test and measurement as a discipline that is foundational to all of science. In fact, I would argue that it has a foundational dignity apart from any particular application just by virtue of the fact that it complements sensory perception. And although the means of test and measurement certainly change over time, I look at the discipline itself as the very root of all science, and that's why I am so passionate about it. The second thing that I hope to communicate is that a philosophical view helps us to judge particular aspects of the discipline of test and measurement. Let's face it, not all test and measurement is good test and measurement, but what's the standard by which we discern that which is good from the bad and the ugly? Well, my own standard, and the standard that I hope to uphold in this class, is that test and measurement is good to the extent that it supports the explanation of reality. So Agilent's claim is that we are the world's premier measurement company, and I hope that our customers hold us accountable to that claim by challenging us to bring products and processes to the market that really do support the explanation of reality. Okay, so now we are in a position to begin looking at instrumented indentation as a specific kind of test and measurement capability. So what exactly is instrumented indentation? I've taken this definition from the first article that I wrote for experimental mechanics, and I'm going to just read it verbatim here. Instrumented indentation testing, which I will often abbreviate as IIT, is a technique for measuring the mechanical properties of materials. It is a development of traditional hardness tests such as Burnell, Rockwell, Vickers, and Nuke. Instrumented indentation testing is similar to traditional hardness testing in that a hard indenter, usually diamond, is pressed into contact with the test material. However, traditional hardness testing yields only one measure of deformation at one applied force, whereas during an instrumented indentation test, force and penetration are measured for the entire time that the indenter is in contact with the material. Nearly all of the advantages of instrumented indentation testing derive from this continuous measurement of force and displacement. So what does all that mean? I have this schematic here. There are certainly other valid ways to control force and displacement, control force and measure displacement, or even vice versa. You could certainly control displacement and measure force. But this is how all of our indentation systems work. So I wanted to present this up front because this is what I have in mind when I talk about force and displacement. This is what I have in my mind. So for you to, get the most out of what I'm saying, this is what you should have in your mind, at least for now, while recognizing that there are certainly other valid ways to accomplish this. So this is a schematic of our hardware. We impose force along the indenter shaft electromagnetically. And what that means is we have a coil that sits within an annular magnet, and we run current through this coil, and that causes a force along the direction of the indenter, and that causes the diamond, it doesn't have to be diamond, but usually it is, the diamond indenter to press into the test material. And so we know the force by the magnitude of current going through the coil. We simultaneously measure displacement. And we do that with this 3-plate capacitive gauge. So we have the 2 green plates here are fixed to the outside world through the housing, and then the blue plate here is fixed to the indenter shaft and moves up and down. And by monitoring the capacitance between the center plate and the outside plate, we know the absolute position of the indenter within its range of travel. Okay, so fundamentally, the way our equipment works is by imposing force electromagnetically and measuring displacement. So force is the independent variable and displacement is the dependent variable. All right, and when we do that, when we press the indenter into the sample, here I have a picture of an indenter. The very apex here is what gets pressed into the material, and although depending on application, a variety of indenter geometries are acceptable, the most commonly used geometry is a three-sided pyramid, and that has the name Berkovich pyramid. And when that's pressed into a material, it leaves a residual impression that looks like this. This is a residual impression in nickel. And what we are looking at during the test is force and displacement. Now, you remember I said that force in our equipment is the independent variable and displacement is the dependent variable. So if we were true to that, we would plot force on the x-axis and we would plot displacement on the y-axis. But tradition just won't have it that way. Displacement goes on the x-axis and force goes on the y-axis, and people just aren't used to looking at it any other way, and so we go along with that. So this is a plot of the contact force between the indenter and the sample and the mutual approach between the indenter and the sample, and we call that displacement. So the origin of this plot at 0, 0 is when the indenter first touches the sample, okay? And then we increase the force, and that moves the indenter into the sample. We increase it, increase the force up to some peak force, okay? And then we start to reduce the force. And we do get some elastic recovery, but we generally do not recover all of the displacement that we achieved. We have some permanent deformation, which allows us to see the residual impression like this, and we have some elastic recovery. All right, so there are two related questions that I need to address from the very outset. The first question is, what makes instrumented indentation different from traditional indentation like Vickers or Burnell or Rockwell? And the second question, which is actually directly related to the first, is why is instrumented indentation called nano-indentation? So I want to take those in turn and then show how they're related. Okay, so what differentiates instrumented indentation from traditional hardness testing? And when I ask this of classes, someone always says, well, you do it at small scale. Vickers hardness test is it leaves a big impression. You can go and look at it under a pretty low-powered microscope. So traditional indentation testing is big, and instrumented indentation testing is small. And that is not the right answer to this question. What makes instrumented indentation different from traditional hardness testing is the continuous monitoring of force and displacement for the entire time that the indenter is in contact with the material. So a traditional hardness test, you apply some force and then you have one measure of displacement. In a Vickers hardness test, you apply a force and then you take the sample to a microscope and you, by measuring the length of the diagonals, you get some measure, you calculate the contact area, and then the force divided by the area is the Vickers hardness. Okay. Rockwell and Burnell use slightly different definition of deformation, but still, in a traditional hardness test, it's one force and one displacement. In an instrumented indentation test, force and displacement are continuously monitored for the entire time that the indenter is in contact with the material. And all of the benefits that we associate with instrumented indentation come from that continuous monitoring. And although I can't, you'll have to be patient with me until we get to it in the next couple sessions, I'll just tell you right now that there are two major benefits. The first major benefit is that it turns out that from this force displacement information, you can actually calculate the contact area. Okay, and you can do a pretty good job of it, and that's actually called the Oliver Farr model. So that's the first really important benefit, is that you can calculate the contact area from just the force displacement information. And the major benefit there is that you don't have to go and measure the contact area microscopically in a lot of practical circumstances. And so not only is that simpler from an experimental standpoint, it also facilitates doing really, really small tests, because you don't have to go after the fact, find the indent, and come up with some reliable way of measuring the contact area. So that's the first benefit. That's the first major benefit of continuous acquisition of force and displacement data. The second major benefit is that it turns out that this elastic recovery during withdrawal allows us to get at the elastic properties of the material, which is really, really useful and really unique compared to traditional hardness testing. So in traditional hardness testing never has and never will give you a Young's modulus, for example. But instrumented indentation testing, because we are monitoring the recovery of the material during the withdrawal of the indenter, does give us the elastic properties of the material, and one of those is Young's modulus. Okay, so I've already alluded to the answer to this second question. Why is instrumented indentation testing also called nanoindentation? Well, the reason it's called nanoindentation is that the fact that we can get at contact area from the force displacement data, that fact facilitates very small scale testing. So because we have this continuous force displacement data, we can get it. We can know the contact area even when the contact is very tiny, and that is what allows us to do indentation, quantifiable indentation on the nano scale. Okay, so I want to point out that in my mind, all four of these are synonymous terms. You will hear this called instrumented indentation, nanoindentation. Also in the literature, you will sometimes see depth sensing indentation and continuous recording indentation. And all of those are different ways of saying we are continuously monitoring the force and displacement for the entire time that the indenter is in contact with the material. You are going to hear me use these two terms interchangeably. I rarely use these two terms, but I might, okay, because in my mind, these are all the same. Now, I do tend to use nanoindentation when I want to emphasize the fact that continuous recording of force and displacement opens up this possibility of doing nanoscale indentation. And I'll use instrumented indentation when I want to emphasize the generality of what we're doing here. In other words, it's not the size that makes it what it is. It's the fact that we are continuously monitoring force and displacement, and that can happen at any scale and has benefits at any scale. Okay, so that summary reason for differentiating between these two terms, but really all four of these things mean exactly the same thing. Okay, so let's talk about just some of the material properties yielded by instrumented indentation testing. The first property that I want to talk about is Young's modulus. I took this definition from Wikipedia. I thought it was really good and really general. So Young's modulus, also known as the tensile modulus, is a measure of the stiffness of an elastic material and is a quantity used to characterize materials. It's defined as the ratio of the uniaxial stress over the uniaxial strain in the range of stress in which hooks want to hold. And that's just a fancy way of saying it characterizes the elasticity of the material within the range of stress, but that characterization is actually appropriate. Okay, it is true for all those times in which it is true. All right. Okay, so that's Young's modulus, and that is one of the material properties that we get from instrumented indentation. And you can see just from this relationship why Young's modulus is so useful. If you're designing with a particular material and you know it's Young's modulus, then you can predict stress for a particular strain. If you have strain and you know the Young's modulus, then you can predict the stress. Vice versa, if you know what the stress in that member is going to be and you're in possession of the Young's modulus, then you can predict the strain in that member. And so from an engineering standpoint, the Young's modulus is extremely valuable design parameter. Okay, the second property I'd like to discuss today, these other three are all going to have to wait for later sessions. The second property I'd like to discuss is yield stress and its four-man alternative, which is hardness. Okay, yield stress and hardness. Yield stress is that value of uniaxial stress at which plastic or permanent deformation ensues. Hardness, which is generally defined for an indentation test as load divided by contact area, is a poor man's quantification of yield stress. It's cheap and easy, and for metals, hardness is directly related to yield stress through a constant, and it turns out that we know empirically that that constant is about 3. Okay, so hardness is directly proportional to yield stress for most metals. All right. Okay, so these are the material properties that we're going to start with. And in the next session, we're going to start to look at how Young's modulus is related to the force and displacement, the contact force, and the mutual approach that is experienced during an indentation test. All right. Now, indentation is not the only way to get at these values, and in fact, it's a rather late coming way to get at these values. So traditionally, if you wanted to know Young's modulus and yield stress, you would fashion for yourself a test specimen with a geometrically simple cross-section. That might be a square or rectangle, or simplest yet, a cylindrical cross-section. So let's just think of this as a cylindrical cross-section, and then we would apply force by some means to both ends of the section to stretch it and watch the deformation. Now, the reason that we would fashion this particular test geometry is because when we apply force in that way, the stress that's set up in this member is uniaxial, okay? And so geometrically, the analysis is very simple. The stress, and the uniaxial stress in this member is just the force divided by the contact area. And then the deformation, we normalize the deformation by taking the change in displacement, the amount that it's stretched, and dividing by the original length of the test section. Okay, so we would get a plot like this. We would get stress versus strain. And remember, stress is the force divided by the cross-sectional area for this geometry, and the strain is the change in length divided by the original length. And what we would see is a plot like this. Okay, if we look at the blue trace, we see some part during the initial part of that test where stress is linearly related to strain. If we increase the stress, we increase the strain proportionally, and that is the regime. That is a regime of elastic deformation, and we can take the ratio of stress to strain, and that gives us the Young's modulus of the material. So we designed this test specimen because it makes it very easy for us to get at the Young's modulus of the material. Okay, and then at some point, if we keep pulling on the specimen and pulling on the specimen, we reach some stress at which we depart from linearity. And the way we depart from linearity is that for a small increase in stress, we get larger and larger increases in strain. And that's because plastic yield or plastic deformation has set in. And so the point of substantial departure from linearity is the yield stress for that material, and that's also something you would get out of a traditional tensile test. All right, and one more thing I would like to point out, because it's going to come into our calculations later, is the Poisson's ratio for the material. A final benefit of this kind of test is that it also allows you to get at the Poisson's ratio, which is another elastic property of the material. For an isotropic material, the Young's modulus and the Poisson's ratio completely define the elastic behavior of the material. And there are other definitions of modulus that you can derive from that, but for an isotropic material, Young's modulus and Poisson's ratio are complete characterization of the material. All right. So the way that you get Poisson's ratio from a tensile test is Poisson's ratio is the ratio of radial strain divided by axial strain. So when you stretch this thing, if you stretch it, you can imagine that this material is going to contract radially. And if you take the radial strain divided by the axial strain, that gives you the Poisson's ratio of the material, the second critical elastic parameter. And likewise, if you compress this material, it's going to expand about its cross section, and so that is also a way to get Poisson's ratio, is the increase in radial strain relative to the strain, the compressive strain in the axial direction. All right, so that's Poisson's ratio. You get Poisson's ratio out of a tensile test. Okay, so the question is, well, if we can get all this information out of a tensile test, why do we need instrumented indentation? And the first answer to that question is because we don't have enough material to do a tensile test. Instrumented indentation arose as a technology because people wanted to know the mechanical properties of thin film. You have a material that you're interested in, and that may be a film sitting on a substrate, and the film may be just a couple microns thick or even thinner. There's no way, at least not easily, that you can gather that film from its condition and fashion a tensile coupon out of it so that you can do a tensile test. It's if it's feasible at all, it's definitely not practical. Okay, so the first reason to do an instrumented indentation test is just because we don't have enough material to do any other kind of test. The second reason to do an instrumented indentation test is that it turns out that material actually behaves differently at small scales. So because the material exists in the form of a thin film, it can behave differently than if that very same chemical material existed in bulk form, okay? And if you're going to actually use the material as a thin film, then you want to measure its properties as a thin film, because generally those properties are going to be different than if that chemically identical material existed as a bulk material. That's especially true for plastic properties, and that's because the constraints of the material dictate the grain size of the material, and grain size dictates how dislocations move throughout the material, and that dictates the plastic behavior. So in general, it's important to remember that especially with respect to plastic properties, the material simply behaves differently because it exists in confined spaces. And so if that's how you're interested in using the material, then that's how you should measure its properties. Now, the final reason to use instrumented indentation or consider it is just for the testing simplicity. The analysis is certainly not simple, but the analysis is well established. And as far as testing goes, it's really simple. You don't have to fashion a pencil coupon. There's no special there's no special sample preparation. All that's really required to successfully do an instrumented indentation test is to present a flat, smooth surface orthogonally to the direction of motion of the indenter. So all you need is a flat surface, and you can do an instrumented indentation test. And what's more is you can do a lot of instrumented indentation tests. You know, you can consider doing tests here and there and all over the surface to really get a good idea of the material properties of the sample. All right, so in summary, the discipline of test and measurement has a foundational dignity in science apart from any application because it enhances and quantifies sensory perception, which is the foundation of all knowledge. As a mechanical test, instrumented indentation complements, it enhances and quantifies our sense of touch. And an instrumented indentation test comprises pressing a hard indenter into a test surface while continuously recording the contact force and the mutual approach or displacement. Instrumented indentation is also called nano indentation, depth sensing indentation, or continuous recording indentation, and all those things mean the same thing. Elastic modulus and yield stress can be obtained by an instrumented indentation test, and relative to uniaxial compression or tensile testing, instrumented indentation has the advantage of being able to characterize small volumes of material with very little sample preparation. All right, well, that's all I have to say for today. I am going to take some questions. First, I wanted to point out that session 2 for this series will occur on the first Wednesday of October, October 3rd, 2012 at 11 a.m. New York time. And of course, all of these sessions are recorded, so you could go back and listen to them in preparation for the second session. I have here the abstract for that session. Basically, we're going to start and look at elastic contact models because elastic contact models specify the ideal relationship between force displacement and elastic properties. Okay, and so to register for that class, you follow that link. This is my suggested reading for session 2. If you want to really be prepared to hear and understand what I have to say, you would do well to read Snedden's article, which you should be able to find in your library. This second article by George Farr, Oliver, and Boston on the generality of the relationship among contact stiffness, contact area, and elastic modulus. And finally, if you have access to Ken Johnson's book, Contact Mechanics, I would suggest that you read his 4th chapter on Hertzian theory. All right, and then you'll be prepared for the next session. All right, so thank you. Again, please feel free to send suggested topics for future sessions through chat or directly to my email. And thank you very much. I'd be happy to take any questions.
And we would like to thank you, Jen, for a very interesting and thoughtful presentation. And we certainly do have questions concerning it. Before we go to the Q&A session, I'd like to ask our audience to complete a short polling survey concerning the presentation. The poll is now open on the lower right side of your console. Please complete each question, and we thank you for taking the time to answer this survey. We do value your opinions on how Agilent can better serve you, and we welcome your feedback on our presentations. And now I'll remind our audience concerning the Q&A process. Of course, you may put your questions in the Q&A box. I will read them, and Jen will answer them. Or if you would like, you may ask questions over the phone line by pressing *1 on your touch-tone phone, and the operator will open your line. All right, and as you're completing the survey, so that we can get to all of the questions, let me go to the first one. Why do we have only limited indentation geometry designs? For example, Berkovich shape, conical shape, Connor shape, flat punch shape?
Well, that's a good question. One of the very important things that will show when we start to look next time at elastic contact mechanics is that the really critical thing is that you have to know the geometry of the indenter, okay? And it has to be fairly easily characterized by functionally. In other words, you have to be able to have a functional representation of the geometry of the indenter. So you wouldn't want just, a jagged thing that's difficult to characterize with a function. Generally, you want the simpler the geometry, the simpler the analysis. If you think of it in light of a tensile test, the analysis for a tensile test is so easy because the geometry is so easy. The analysis for an instrumented indentation test is more challenging precisely because the geometry is more complex. So the more complex you make that geometry by the tip you choose, the more challenging the analysis is going to be. And so the analysis is very well worked out for simple geometries such as a flat punch, such as a sphere-tipped indenter, a cone, or pyramid. But that's really about the extent of it. So it doesn't mean that there aren't reasons to use other geometries. It's just the analysis is going to be very challenging, and so you have to be sure that you have a very good reason for selecting some other kind of geometry.
Thank you, Jennifer. Our next question, first of all, thank you for the exhaustive presentation. And here's a simple question. Did you record the variations of the nano-indentation's values related to the measurement surface's orientation toward the main crystallization plans?
Well, for the only force displacement curve that I showed in this presentation, the material was fused silica, which is isotropic, so there's no difference in orientation. That's why we choose it as a standard. However, there are a number of publications. I can think of one in particular where people have, I can think of one where the researchers looked at beta silicon nitride, which has a hexagonal structure, and they indented all kinds of a variety of orientations, and they were whiskers, and they looked at the shape of the hexagon to give an indication of the orientation with respect to the indentation orientation. And from that, they were able to deduce the modulus in the two directions for that hexagonal structure. You could find that article by just searching on beta silicon nitride. One of the co-authors was my husband, John Hay. So if you look for beta silicon nitride and John Hay. You'll find that, and you can see the tack that I took. I think George Farr was also a co-author on that.
All right. Before we move on to our questions, let me just check with the operator to be sure there's not anyone in the phone queue.
I'm showing no questions in queue.
All right. Is it possible to measure internal stress in DLC thin films with nano indentation?
I think the answer to that is no. But if somebody would like to point me to some references, I'd be happy to take a look at it for a future session. I think the best way to measure residual stress in DLC films is by wafer curvature, which is a completely different and perfectly valid mechanical testing technique.
All right. For the indentation curve you showed today, does the indenter tip oscillate during the indenting or just gradually ramp up to the max force?
What I showed was semi-static indentation data, and although we will certainly get into the kinds of tests that you can do by oscillating the indenter, that is not going on here. In other words, we are semi-statically ramping up the load and measuring the associated semi-static displacement. This particular test did not involve any oscillation of the indenter. Okay, that's a more advanced technique, and we're going to get to that down the road.
All right, our next question. When using instrumented indentation testing, are the conversion from Martin's hardness to Vickers valid as reported using various instrumentation for IIT?
That is a great question, and we are going to get into that. You can, of course, calculate a Martin's hardness from an instrumented indentation test. That's prescribed in ISO 14577. But what you really have to pay attention to is that for many materials, especially metals, the hardness that you measure depends on the strain that you're imposing in the material by virtue of the test. So, for example, because those materials increase their yield stress in response to strain, okay? If you have an indenter that's sharper, like a cube corner indenter, on metals, you will generally measure a higher hardness on the material than if you had used a Berkovich indenter, okay? And that is because the cube corner indenter is causing a higher strain in the material, and so you measure a hardness that's proportional to a higher yield stress. Now, in some materials, that doesn't matter. Materials that don't have any mechanism for work hardening, that doesn't matter. So that's really what you have to pay attention to. What you'd have to do is look at the details of a Martin's hardness test or whatever other kind of test that you wanted to do. And if you wanted to mimic that with an instrumented indentation test, what you'd have to do is mimic the test conditions of the original as closely as possible. But you have an instrumented indentation in general, you have a wide latitude in the kind of test that you perform. You know, you have a wide latitude in what kind of indenter geometry you select. You have a wide latitude in the way that you impose force and measure displacement and so forth.
Thank you, Jen. Is there a way to quantify the effect of the electromagnetic forces on the specimens? Do you think that will have an effect in a magnetic material?
I mean, the simple answer is no. I haven't seen that. The head pretty well shields that coil, and I think that's why we don't see it. The head is the casing for the head is metallic, and so that provides a very nice shield for the electromagnetic coil. Yeah, we just haven't seen that. So it's an interesting phenomenon, and it's a good question, but I haven't seen it come up practically.
Okay. Are we able to extract with this technique mechanical information on multi-layers, thin film structure?
Yes, it is fairly straightforward now to extract the properties of a single film on a substrate. That's pretty straightforward, and we will definitely get to that. It gets more complex as you have multi-layers, and generally what the approach that you have to take is that you have to say, okay, all the layers below the top layer act in some composite way, and I'm just interested in the top layer. I don't know of a way, if you have, say, 5 layers in a stack sitting on silicon, I don't think that instrumented indentation can be used in a single test to extract the properties of each of the 5 layers. You have to be a lot more clever than that. For example, you might have to build up the stack. Like you might have to have the first layer on the silicon and test that, then then add the second layer and test that, and so forth. You can't just get it. You can't get the properties of the individual layers just by pushing the indenter in the top of the stack all the way down to the substrate. That won't work.
All right, and before we continue with our questions, I'd like to take a moment here to make a few announcements to our audience. Following the seminar, you will be receiving an email with a recording link for today's presentation, as well as in a separate email, I will be sending you a PDF copy of the presentation. I know some of you have asked about the publications and the papers that Jenny has written, so all of that information will be sent to you. In addition, as you know, this is going to be an ongoing series, and the slide presently displayed tells you again about Session 2 on elastic contact mechanics, which will be coming up on October 3rd. And let's see, we are close to our time, but there are a few questions. So, Jen, if you're willing, I will go ahead and ask those. What is the difference between hardness and stress?
Well, hardness has the units of stress. Hardness is load divided by area. It has the units of stress. But what you have to think about is how that stress relates to the components of stress in a simpler geometry. And that's really the challenge of instrumented indentation. You can't just say how does hardness relate to stress. Hardness is itself a stress. I mean, that is what hardness is. It's a stress. But how that relates to components of shear and normal stress in say, an infinitesimal square is not easily addressed.
All right. Let me check. Jen, I just want to be sure that you don't have any questions that I didn't have, as sometimes questions are sent just to presenter. I think we have answered all of those in the Q&A box, and I certainly have gone through all of mine in the chat box.
I do not have any other questions in mind.
All right, and since we are over our time just a little bit, I would like to now close the e-seminar on behalf of the Nano Measurement Group at Agilent Technologies. We thank you for joining us today and for your participation, and we certainly hope to see you at Session 2 of this series. We will leave the question box open for a few more minutes to receive any feedback or additional questions, which will be answered via email. For now, we're going to close the phone line. We thank you once again for attending, and from Agilent Technologies, we wish you a good day.
Ladies and gentlemen, this does conclude your conference.